Thermal interface materials for improving thermal contacts. This is Deborah Chung at Buffalo. Overheating of microelectronics and cell phones, that's a big problem. And the heat source is very often the microprocessor. So the overheating limits the reliability, also limits the further miniaturization, and limits the power. Not only microelectronics and cell phones, but also light-emitting diodes needing heat dissipation, and also electric vehicles with battery pack. The battery needs the heat dissipation. Now, how to improve the heat dissipation? Let's say you have a microprocessor and a heat sink above, and you need to improve the thermal contact between these two. So one puts in between the two a thermal interface material. And a thermal interface material is abbreviated TIM, and most often it is in the form of a paste called thermal paste, because the paste is easy to dispense and also it's low in cost. TIM market size is increasing, particularly large increase is projected from now to 10 years from now. It's projected to exceed $7 billion by year 2036, with annual increase of around 10%. And the electric vehicle battery is one big area. Also, the 5G is another big area. The application sectors include consumer electronics, electric vehicles, data centers, advanced semiconductor packaging, advanced driver assistance systems sensors, 5G infrastructure, aerospace and defense, industrial electronics, and renewable energy systems, also medical electronics. In particular, consumer electronics include, they are the largest market segment, and they include smartphones, tablets, and wearable devices. Now, high thermal conductivity for the thermal interface material alone is not enough. The reason is no surface is perfectly smooth. So you always have some ups and downs, so some air pockets at the interface. And so the thermal interface material better enter all these little valleys and displace the air out. If you have insufficient conformability of the TIM, you would have air pockets left at the interface, and air is a thermal insulator. TIM1 and TIM2. TIM1 is applied between a flip chip integrated circuit and a heat spreading lid. TIM2 is applied between a finished electronic package and a heat sink. The material requirements are similar for TIM1 and TIM2, and this illustrates TIM1 and TIM2. The left bottom drawing is easiest to see, TIM1 and TIM2. For data centers, liquid cooling is the main method of cooling, but it uses a massive amount of water. That is another problem. And TIM2, although not shown here, is needed. When you have without the TIM at the left and with the TIM on the right, you see that the thermal resistance at the interface is diminished, so that the temperature drop at the interface is reduced when you have the TIM present, as opposed to the TIM not being present. So the measurement of the temperature drop, as shown on the right diagram, is one way to measure the thermal resistance of the interface. That's describing the effectiveness of the TIM. This shows that the temperature drop occurs not only within the TIM, but also at each of the two interfaces between the TIM and the adjoining material. So there are three temperature drops here. Okay. The design principle of thermal interface material has long been one thing, which is high thermal conductivity. However, I put forth that there should be another principle, which is very important, and that is conformability. And that results in a paradigm shift in the design principle of thermal interface material. I raised that point back in 2003. The conformability refers to the ability to conform to the surface topography of the adjoining surfaces. I should stress that conformability requires micro-scale kind of conformability. That is different from macro-scale kind of resiliency or macro-scale kind of compressive modulus being low or soft. Because the little valleys in the surface topography can be in the micro scale. Silicone, for instance, is resilient and soft, but typically not conformable in the micro scale due to the long length of the molecules. Spreadability is also important as the thermal resistance increases with the thickness of the TIM. Ideally, the amount of the applied thermal paste is just enough to fill the valleys in the surface topography of the adjoining surfaces. Now, the properties that affect TIM performance include the conformability, the spreadability, and the thermal conductivity. The thermal paste has in it a solid component and a liquid component. We want both the liquid and solid components to be conformable. Carbon black is advantageous in its squishability, which results in high conformability and high spreadability. In addition, it is thermally conductive. Also, it is hydrophobic, so that it's easy to disperse in organic liquids. Also, it's very cheap. So using carbon black, I've developed a thermal paste which excels due to its conformability, with both the solid and liquid parts being conformable. This is me holding the black bottle, and it's black because it's carbon black thermal paste, and this was reported by me in 2003. The thermal contact conductance, which is the inverse of the thermal contact resistivity, increases with the TIM thermal conductivity with all other conditions fixed. That's kind of obvious. However, too high a filler content results in low conformability, though high thermal conductivity. So a compromise is needed between conformability and thermal conductivity. In case of carbon black, the optimum is 2.4 volume percent, not very high. Okay. And the prior design paradigm is to maximize the filler content in order to maximize the thermal conductivity with no consideration of having an optimum. Now, the vehicle in the paste is also important. It should not be volatile. It should be organic and not necessarily polymeric, because we don't want long molecules. The small molecules is needed to enter the small valleys in the surface topography. Ability to withstand elevated temperatures up to, say, 100 degrees C at least. Examples include polyol ether and polyethylene glycol. And much of what I'm going to talk about involves polyol ether. Now, the roughness of the adjoining surfaces matter a lot. Higher thermal conductivity is needed for rougher adjoining surfaces due to the larger distance of the heat path. The smoother the adjoining surfaces, the higher is the thermal contact conductance due to the smaller distance of the heat path. So it'd be better to polish your material to make it as smooth as possible. The testing conditions include these: the roughness of the adjoining surfaces, the thickness, the thermal conductivity of the joining materials, and the pressure. All conditions must be controlled, otherwise comparison cannot be made among results obtained in different laboratories. First, consider roughness of the adjoining surfaces. This shows the thermal contact conductance versus the roughness with all other conditions fixed. And you can see that the greater the roughness, the smaller is the conductance. And also the smaller is the fractional valley filling. Thickness of the TIM, another test condition. And here shows the conductance versus TIM thickness, with, again, all the other conditions fixed. The greater the TIM thickness, the smaller is the conductance, and the greater is the fractional valley filling. Here shows the interfacial conductance of the interface between the TIM and the copper block, which is the mating material, the adjoining surface. This interfacial conductance is shown on the horizontal axis, whereas the overall thermal contact conductance of the sandwich is shown in the vertical scale. And the two relates, obviously. But note that the interfacial conductance is higher than the thermal contact conductance of the sandwich by a factor of 12. So we have to make sure that when we read a paper, we are distinguishing between these two parameters. Next, pressure, another testing condition. Pressure application promotes the thermal contact conductance, and prior pressure application also helps in case of carbon black paste, at least. And this shows the thermal contact conductance versus pressure with all other conductions fixed. The higher the pressure, the higher is the thermal contact conductance. And this is due to the slightly decreased thickness due to the increased pressure. Next, how do we assess the TIM performance? The testing of TIM performance must involve the measurement of the thermal resistance of the sandwich that consists of the two adjoining surfaces and the sandwiched TIM. A common pitfall is the use of the thermal conductivity of the TIM as tested without the sandwiching to assess the TIM performance. Thermal contact conductance is the inverse of the thermal contact resistivity. Temperature rise of operating electronics is good for a particular application circumstance, but is not good for material characterization. For thermal contact conductance measurement, there are two methods, steady-state method and transient method. The guarded hot plate method is the steady-state method, with the heat flux being vertical, and the TIM is sandwiched by two, say, copper blocks, each block having two holes for inserting two thermocouples. So you have A, B, C, D, 4 points to measure the temperature versus the position in the vertical direction. The laser flash method is the transient method. You have a pulse of laser and flashing on the sandwich. And on the backside of the sandwich is a thermocouple to measure the temperature rise. And the rate of the temperature rise reflects the thermal diffusivity, which relates to the thermal conductivity, or the thermal contact conductance in this case. Now, the thermal paste fillers include carbon black, graphite nanoplatelet, graphene, also carbon nanotube, graphite particles, ceramic particles such as nanoclay, zinc oxide, and hexagonal boron nitride, also fumed alumina particles. Now, carbon black and graphite nanoplatelet and graphene, let's talk about these first. Carbon black, as I said, has a nanostructure in which you have nanoparticles making aggregates. And these nanoparticles are just connected by van der Waals forces. So it's very easy to squish down the aggregates. And shown at the left is before the squishing. The right is after the squishing, and you can see the squishing. It's due to the easy movement between the nanoparticles in an aggregate. This is carbon nanoplatelet. It shows pretty thin platelets. But this is not graphene nanoplatelet. It's not graphene, okay? Because the thickness is not below that of 10 layers of carbon. Very often, the thickness is not even known. So one cannot say that it's graphene if you don't know the thickness. The terminology is that you can have a monolayer graphene, 1 layer. You can have 2 to 10 layers, and that's called few-layer graphene. You can have 11 to 30 layers. That would be not graphene because it's more than 10 layers. That would be graphite nanoplatelet, or just call it graphite. Okay. The nomenclature is confusing because graphene is a very fashionable word, much more fashionable than graphite. So people want to call their material graphene even though it is graphite and not graphene. Shown here is the comparison of carbon black and graphite nanoplatelet for different volume fractions, showing the thermal contact conductance for the rough and smooth copper surface case, and also the thermal conductivity. And you can see that for carbon black, the optimum carbon content is 2.4 volume percent. Okay? The 2.4 gives the highest value of the thermal contact conductance, whether for rough or thin or smooth surfaces. For graphite nanoplatelet, on the other hand, the optimum content is either 1.2 or 2.4 volume percent. The thermal conductivity is higher for graphite nanoplatelet than carbon black. The thermal contact conductance is higher for graphite nanoplatelet than carbon black for rough surfaces, but is higher for carbon black than carbon nanoplatelet for smooth surfaces. And this this is because higher thermal conductivity is more important for rough surfaces than smooth surfaces. And the graphite nanoplatelet has higher thermal conductivity than the carbon black case. The thermal contact conductance is much higher for rough surfaces than for smooth surfaces than rough surfaces, regardless of the thermal conductivity. Next, consider carbon nanotube. They tend to lie down. So the high axial thermal conductivity of nanotubes is not adequately exploited. The criteria for choosing the filler include thermal conductivity, conformability in the microscale, small unit size as needed for conformability and spreadability, and preferably not electrically conductive. The thermal conductivity is more important when the adjoining surfaces are rougher. Carbon black and fumed alumina both have the morphology of aggregates of nanoparticles. So these two are the only two in the list that are squishable. All the others are not squishable. This is the carbon black, aggregates of nanoparticles. And this is fumed aluminum oxide, also is in the form of aggregates of nanoparticles. So the fumed aluminum oxide is similar in structure and conformability as the carbon black, and it's attractive for being not an electrical conductor. Now, there is low structure carbon black and high structure carbon black. Low structure means the aggregate size is smaller. Low structure is more effective for TIM due to the superior conformability, even though the high structure promotes the thermal conductivity. Here it compares the thermal contact conductance for these 4 fillers: carbon black, graphite nanoplatelet, nanoclay, and fumed alumina. Carbon black and fumed alumina give similar thermal contact conductance, as you can see, for both rough and smooth surfaces. Nanoclay, in red, the superiority of nanoclay for smooth surfaces is attributed to the submicron bond line thickness. The inferiority of nanoclay for rough surfaces, as you can see, is due to the low thermal conductivity. Nanoclay is also attractive for its being not conductive electrically. Attraction of TIMs that are not conductive electrically to avoid short-circuiting in case that parts of a TIM drop out. However, electrical non-conductivity is not required for TIMs. Now, how to render a thermal paste not conductive electrically? Well, one is to use a non-conductive filler, such as the fumed alumina or nanoclay. Another way is the combined use of a conductive filler, such as carbon black, and a non-conductive filler, such as fumed alumina, and the non-conductive filler breaks up the conductive path. Now, thermally conductive adhesive involving epoxy or silicone is attractive. Okay. Adhesive thermal paste are thermal pastes that are adhesives, and they are preferred to those that are not adhesives, since there would be no need for fastening to keep the TIM sandwiched by the adjoining surfaces. The conformability, spreadability, thermal conductivity, and reworkability all tend to be compromised by the inclusion of an adhesive constituent. Work on adhesive thermal paste is little compared to that on non-adhesive thermal paste. This shows a thermal pad at the bottom here between the heatsink and the CPU. Okay. And this, the pad is usually called a gap-filling thermal pad, and they can be available in this form, in films and tapes. The gap-filling material between here is the battery pack and the cooling plate. It's needed for electric vehicle battery heat dissipation, and is particularly needed for fast charging. And liquid dispensed gap-filling materials, like here, like a snake, this gives high conformability and variable thickness. However, the gap between adjacent lines of this pattern are not attractive, because the empty spaces would be just air, which is a thermal insulator. Now, why need gap filling? Non-parallel adjacent surfaces, curved adjacent surfaces, even a gap between the adjacent surfaces. The requirements of gap-filling materials are these: conformability, thermal conductivity due to the large distance of the heat path, and the thickness not excessive. The shortcomings of gap-filling TIMs include low thermal contact conductance, low compared to the thermal paste, due to the large thickness, limited thermal conductivity, and limited conformability. The gap-filling TIMs are basically these materials: elastomer with thermally conductive filler, metal foil, which is attractive for high thermal conductivity, but coated with thermal paste on both sides. Flexible graphite, attractive for low elastic modulus, coated with thermal paste on both sides. And carbon nanotube array. Let's first consider flexible graphite, coated with thermal paste on both sides. Flexible graphite is made from graphite flake. The flakes are intercalated. On the left is after intercalation, and then on the right is after the exfoliation of the intercalated flakes. And the exfoliation causes huge amount of expansion, resulting in something looking like a worm and having this accordion kind of structure, cellular structure. This is actually called a worm, which is derived from a flake after tremendous expansion along the axis of the flake, vertical axis. And this is that exfoliated graphite with the cellular structure. When you have a pile of these worms, you can compact that in the absence of a binder. Due to the cellular structure, you have mechanical interlocking, thus resulting in a sheet called flexible graphite. The attractions of this sheet include these: very high in-plane thermal conductivity, moderate through-thickness thermal conductivity, resilience in the through-thickness direction, and temperature resistant, chemically resistant, since this is all graphite, and low in thermal expansion coefficient. Flexible graphite is widely used as a heat spreader because of the high in-plane thermal conductivity, but it is also used as a gap-filling TIM. Shown here are various gap-filling materials, comparing with and without carbon black thermal paste coating, and also comparing with two commercial gap-filling materials at the bottom. The thickness is indicated. Thermal contact conductance for rough and smooth surfaces are also indicated. And the pressure is held fixed, and the surfaces are copper fixed. And shown here, the carbon black thermal paste coating helps for both the aluminum foil. The coating helps. For the flexible graphite, the coating also helps. The aluminum foil is better than the flexible graphite because it is thin and high in thermal conductivity. For both the rough and smooth surfaces, the aluminum foil is better, whether with or without the carbon black thermal paste coating. The commercial thermal pads, Thermagon and Chromerix, are inferior due to their large thickness. You see the thickness is very large, and that results in very low thermal contact conductance. The aluminum foil with the thermal paste coating is the best in this list. If a larger thickness is needed, flexible graphite is the best. Shown here at the left is the unmodified flexible graphite. On the right is flexible graphite with carbon black thermal paste penetrated in the flexible graphite during the making of the flexible graphite. This penetration is not the same as the coating that I mentioned in the last slide. And here is a composite of flexible graphite with solder particles incorporated again inside the flexible graphite. So these are further modifications of flexible graphite. Shown here are the flexible graphite with carbon black penetration and flexible graphite with solder. And you can see that the thickness is substantial because it's flexible graphite, and the thermal contact conductance from 14 to 17, it is note that there's no coating, right? This is all inside, carbon black inside, the solder inside, and the thermal contact conductance for the rough case is shown here. 14 to 17 is the best. It's the best in this list. And the very best is the 17, which is a flexible graphite with the solder particles incorporated. How about carbon nanotube array as gap-filling TIM? The CNT array is also known as vertically aligned CNTs. And you can see it's vertically aligned. attractions are high thermal conductivity of each carbon nanotube in the array, and the substantial length of the nanotubes, making the array attractive as a gap-filling material. However, there are problems. One is that the nanotubes are not all of the same length. Say the top is not flat. So you need to have an extra layer of something at the top because the top of the array is not flat. Now, the nanotubes need to be grown catalytically at high temperatures from a substrate that has the catalyst particles on it. And that high temperature of the growth limits the kinds of substrates that qualify. And that means that one needs to transfer the array after the growth to another substrate. And that transfer is not simple. So the problems with the CNT arrays are these. The presence of air between the nanotubes in the array makes the overall array limited in thermal conductivity. The length of the nanotubes are not uniform, so the upper surface of the array is not flat and is not conformable. The upper surface needs an interlayer, such as a solder layer. The thermal conductance is not high. The thickness is large. That's good for gap filling. The CNT array growth involves catalyst, needs to be performed at high temperatures and requires high temperature substrates. And the transfer of the array from the growth substrate to another substrate is not simple. Also, the CNT array is very expensive. Next, consider phase change material, or PCM, and the phase change is melting. Through melting, the tin becomes conformable, and at least more conformable, and so the tin performance becomes better. The PCM, or phase change material, functions above the melting temperature, and the molten state provides the fluidity for conformability. The melting temperature should not be too high compared to the relevant temperatures. The melting transition must be reversible. The flow of the molten material is of some concern. There are many types of phase change materials, but we want those at the low temperature range typically. So paraffin or wax is an example. This is the DSC thermograms during heating and subsequent cooling. The thin line is a phase change material with boron nitride filler, and the bold line is without the filler, and the boron nitride reduces the undercooling during solidification, and that's good. And this particular phase change material is 98% weight thiopropionate antioxidant with 2% weight sterically half-hindered phenolic antioxidant as the matrix. And this antioxidant PCM as the vehicle of the thermal paste give these values of the thermal contact conductance. The conductance is higher for boron nitride than carbon black for rough surfaces, but is higher for carbon black than boron nitride for smooth surfaces. The values are lower than those obtained using non-PCM, like polyester, as the vehicle. Okay, so the PCM performance in terms of the thermal contact conductance is not that great. Shown here is the viscosity of 3 PCMs at 2 shear rates. The antioxidant PCM, which is the bottom row, has higher viscosity than the paraffin wax, which is the upper row. The high viscosity reduces the seepage tendency. Here shows the thermal contact conductance versus temperature for the antioxidant. It's the wax as the PCM filled with 4% boron nitride. And you can see the thermal contact conductance drop as you heat, and then further heating causes the conductance to rise. The drop may be due to the oxidation of the copper surfaces sandwiching the tin. The rise afterward it occurs after the start of the melting at 48 degrees C for this wax. Now, phase change material is also available in the form of a thermal pad. Shortcomings of phase change TIMs include these: low thermal conductivity, such as 0.25 watts per meter K for paraffin case, limited conformability, melting temperature choice limitation, undercooling in solidification, thermal cycling ability limitation, and seepage tendency. However, shortcomings of thermal paste are these: they cannot withstand high temperatures, which are encountered in power electronics. Also, limited thickness. Liquid metal tin can be, say, an alloy containing gallium. In this example, the melting temperature is 3 degrees C, so it's a liquid at room temperature. The thermal conductivity is very high because it's a metal. But however, it's only good for copper or nickel-plated materials, not good for aluminum due to the reactivity. In general, liquid metal TIMs can be solders, indium, gallium, and others. They have high thermal conductivity. They include metals that can withstand high temperatures, but the reactivity of the molten metal with the adjoining surfaces is a big concern. And the reactivity also limits the solderability. And the seepage of the molten metal is a concern. The melting temperature choice is limited, and the dispensing tends to be a bit complex. Here is a list of the thermal contact conductance and thickness values of TIMs, and it's listed in order of decreasing thermal contact conductance. The nanoclay thermal paste is at the very top, okay, followed by gallium-based material, carbon black paste, CNT array, fumed alumina paste, ceramic thermal paste, solder graphite composite, and so on. And it goes on. The lower the list, the worse it is. However, not shown in this list is very new work reported by Cheng in 2025. It is liquid metal infused copper nanowire array. It is a copper nanowire, 0.8 micron diameter array on each side of a copper foil with the liquid metal infiltrated into the arrays. This TIM has thickness 60 microns. The thermal contact conductance reaches 1 times 10 to the 6 watts per meter square K, which is higher than that of the best in the list that I showed you. The roughness of the copper blocks sandwiching the TIM is not reported. As I said, the roughness needs to be specified, otherwise you cannot compare apple with apple. But the roughness is not revealed in this paper. The thermal conductivity is very high since it's all metal, 70 watts per meter K, and the thermal contact conductance is higher than the value of 4 times 10 to the 5 watts per meter square K for the best material in my list just shown, and that best material is the nanoclay thermal paste. But again, the comparison might not be fair because the roughness is not revealed in this 2025 work by Cheng. This material is better than the CNT arrays in the performance. However, there's tendency for the copper nanowires to be deformed plastically upon use. And the reactivity of the liquid metal is of concern, and also low reworkability, and it's also expensive. Most recent work on TIM development focuses on composite structures, such as what I just said, liquid metal infused copper nanowire array, also CNT array without and with phase change material, also solder graphite composite, skin core layered polymer matrix composite, graphene vertical array with and without metal caps, graphene hydrogel with phase change material, CNT paper, carbon fiber vertical array, graphite powder with CNT, vertical graphene with horizontal graphene top and bottom, graphene CNT aerogels. This shows the annual number of English journal publications on TIMS, the tremendous growth from 2003 to now. My pleading, controlled measurement of the thermal contact conductance, meaning controlled roughness, pressure, and sandwiching material composition. Otherwise, we cannot compare apple with apple. The thermal conductivity alone should not be used as the performance indicator. This would allow meaningful comparison of the performance of various TIMs, particularly from various research groups. The status of the field of TIMs. The TIMs market is rising greatly towards $7.5 billion in year 2036. The research field is growing tremendously with almost 7,000 publications in 2024. Most recent research focused on TIMs with complex composite structures with little attention on thermal pastes. Recent intense research on CNT arrays, which turn out to be not attractive in practice, in spite of the high thermal conductivity of the CNTs. The highest reported thermal contact conductance, 1 × 10⁶ watts per meter square K, is exhibited by copper nanowire array with liquid metal infiltration. Among thermal pastes, the highest is 4 × 10⁵ watts per meter square K. For gap-filling materials, the thermal contact conductance is lower than that of thermal pastes due to the larger thickness. The science of TIMs is insufficiently recognized in the industry or research field. Numerous TIM products in the market and a substantial fraction of TIMs research publications report the thermal conductivity, but not the thermal contact conductance. Numerous reported TIMs cannot be compared to other TIMs in terms of the performance due to the absence of thermal contact conductance results. Liquid metal TIMs suffer from their reactivity in spite of the high thermal conductivity. Suggestions for future work: more attention on thermal pastes as opposed to TIMs with complex composite structures. Thermal pastes that are adhesives, TIMs that are not conductive electrically, gap-filling TIMs with thickness exceeding 50 microns, TIMs with high temperature use, capable of high temperature use. More attention on TIMs that are cost effective. Thank you for your attention.